The first operation we might perform on the binary search tree, not surprisingly, is to search through it. Let's see exactly how we do it. And we are always given some node P, so this will be the root of certain subtree. And we want to locate a particular node whose key matches K. So this will be actually very important before I show you the code. You want to make sure you understand for every node in the tree, they actually store an entry which contains the key and also the value. But whenever we want to do for searching purpose, we're only matching the key. We don't normally match for the value. So there's a reason for that. I can tell you the reason right away, but you can think through it. Whenever we talk about searching through the key, it's because the key values, according to the search property of the binary search tree, will be somehow sorted when we do the in-order traversal. This is a very important property that we already learned about. Right? Again, whenever you want to do any searching through the tree, you are only matching the key value rather than the data value. The data value is only for storage, but for the key, it's actually for searching purpose. That's why they're called search keys. And I'll try to revisit this point whenever possible. Let's now take a look at the implementation. And this will be the full implementation for the search. And let's now go over here very quickly, and then I'll just annotate some insights you should really notice. The method here is going to return some BST node. So that's kind of the result rather than Boolean. You might be wondering, isn't search supposed to tell us whether or not true or false the key actually exists in the tree? In this case, the search will be serving as the basis for insertion and deletion as well. So that's why we are returning a BST node rather than a Boolean value. You will see exactly why. Okay, and for now, just remember, when we talk about the return value for the search, it's not going to be Boolean. So this will be a little bit different from the binary search on the sorted array that we spoke about earlier. So rather than returning a Boolean, we're going to return some BST node. And the BST node over here may be internal or external, depending on what the search result is. I will talk about it as well. That's the result I would like to annotate on the paper as well. Just bear with me. What about the input value? The input value will be, number one, is going to be the root of certain tree, which is called a P over here. And also the key value that we want to search for. And remember, always we assume the key is going to be an integer. And we simply initialize the result of the node that's going to be returned to be just null to begin with. And we say that if the P is already external, we're just going to return the P as well already, right? Directly. You can think about it's more like a base case. By the way, the searching through the binary search tree will be a recursive method. That's why we have to have at least one base case. And whenever we simply return some P that is external, in that case, it will be considered as unsuccessful. We'll visualize this in a moment. And also we say that if P.getKey is already equal to the K we're looking for, in that case, it will be considered as a successful search. And you can see one thing that's implicit over here. The P over here is not really satisfying P that is external. What does that mean? That means P is internal. In the case of successful search, that means the P that we are returning as a result will be internal. For unsuccessful search, it will be P that is external. That's some insight I will try to annotate as well, just to emphasize. It's really important. If you want to ask me about the number one point to note about binary search tree searching process, this will be the number one insight. All right, let's talk about the two recursive cases. If the K we're looking for is strictly smaller than the root key, in that case, we want to search through the left subtree. Otherwise, if the key we are searching for is actually strictly larger than the key of the root, in that case, we should really recursively search on the right subtree. This part over here is really too similar to the binary search tree that we did earlier when we talked about a recursion on the sorted array. You're actually right about that. However, I would like you to maybe hold that thought, because I really want to compare how you can do search through a binary search tree versus doing a search through a sorted array. These two are kind of similar and almost identical process, but you do actually have to be careful. One is about searching through the non-linear structure like a tree. The other one is about searching through some linear structure like an array, but they are not exactly the same. That's something I would like to talk about either at the end of the current part or the next part. We'll see how the timing goes. All right, so that's a very pretty much detailed walkthrough about this method over here. And let me just try to annotate what I just said earlier. And we'll talk about the running time for this search process a little bit later. And for now, let me just annotate what I said earlier. There are two base cases. Base case number one, when the key of the current root is exactly equal to the k, in that case, that means we have a match. That's successful search. In this case, the P over here is guaranteed to be internal, right? I want to make that distinction over here. So the P over here is an internal node. Internal node that's going to be returned. On the other hand, if you look at the first case over here, if the P that we are looking at right now, currently the root is actually external. In that case, we're going to assign P to the result to be returned. In this case, it's the opposite. So this will be unsuccessful search. I'll visualize both cases in a moment. Just bear with me. But I want to make this annotation right away over here. Okay, maybe I can draw better. So this will be actually external node. Right, so it's really important for you to see in the case of unsuccessful, it's going to be returning some external nodes at the leaf level. And if you actually got some match, that will be successful search. In that case, it's going to return some internal nodes somewhere in the tree. Definitely not the leaf node. And of course, these two are simply just the recursive cases. And it should really make sense to you about getting to the left or getting to the right. If you have any doubts, maybe you will get your answer when I try to trace the code together with you, or at least try to trace visually. Alrighty, let's now go back to the slide to see if I got anything missed. And the next part is really about to give you some visual illustration about how the search can be done. I will try to do two kind of tracing for you. One will be just tracing on the diagram like this. I'll do two cases for you. One successful, the other one unsuccessful search. And then I'll try to trace some Java code together with you so that later on when you get to the next two operations for insertion and deletion, you will be able to implement those two operations in Java on your own. All right, let's now switch back. Okay. And the first case, I will let's say I would like to search for the key 65. Somehow you can see 65 is actually over here, so that should be a successful search eventually. On the other hand, the second case, I want to search for 68. 68, you can check, it doesn't really exist in this tree over here, meaning that eventually it's going to be a failed search. However, even though it's a failed search, we want to return something that would be useful for any further use, especially for insertion. I'll talk about it when I get to the insertion, but let's just talk about these two cases. Okay? And don't forget, it's assumed the tree is binary search tree. That's the very important assumption. Every input is a binary search tree, meaning that the search property is actually satisfied, right? Otherwise, it wouldn't be called a binary search tree, would it? Let me lay out that assumption over here, and then we're going to talk about how the search is going to go, step by step. We're going to start with 65, right? 65 is the key we're looking for. And for simplicity, we're only listing the key value for every entry. For the data value, we just omit that. It's not relevant to our discussion over here. But don't forget, they actually exist in the BST node. Just don't forget, you can see in the earlier notes, we talk about the structure for every BST node. We definitely should really include the key and the value. But for visual tracing, sometimes we might only need to show the key, but values still exist. They're just not shown in the diagram. All right, let me go back over here. All right, let's try to do it. So we want to search for 65. You can see stuff on the root, 65, apparently it is larger than 44. So if it does exist, we must go over to 44. We definitely want to go over to the right. And why is that? Why would it be safe to actually go to the right if 65 ever exists in the tree? Why don't we have to go to the left to recur on this side as well? The reason is because due to the search property over here, every node in the left subtree of 44 is guaranteed to be strictly less than 44, according to the search property. So that's why if 65 must exist somewhere, it must be existing in the right subtree. Of course, it may be that 65 does not exist, but if it does exist, it must be on the right subtree. It's a very important logical decision you have to make, right? For the first one, let me write it down over here. So for this part over here, because each or maybe every the key of each node in the left subtree of 44, right? I'm just calling this node 44, must be such that it's strictly less than 44. And this is according to the assumed search property. And we have to apply this kind of property for every level of search. Assumed search property. Right, it's so important to really get this straight, right? And we're gonna apply this one here for every step over here, right? So what we're gonna do is we're gonna go to this particular. We go down one level. Every time you try to do a recursive call, you just go down one level in the tree. And just remember this insight as well, because later on we're gonna use this insight to calculate the running time for the binary search tree. Well, to calculate running time for search through some binary search tree. Right, so now the current key is now 88, right? 88 over here. And where should we go? 88 apparently is not 65. Should we go to the left or should we go to the right? Apparently 65 is actually strictly less than 88. So we should go to the left over here. And then the root now is 65, which is exactly equal to the key we're looking for, which is 65. So now we are done. Ultimately, this will be the node to return. Okay, so this, let me just make it explicit for you. Okay, so for this one over here, let's make a node over here. It's a successful search. In that case, internal node storing 65 is return. Right? This kind of corresponds to the insight I said before. Remember I said before, in general, if it's a successful search, in that case, we're going to return some internal node. That's exactly the internal node we are returning over here. Right? Let me just highlight it. Internal node is going to be returned. Right? Case number one. Let's take a look at case number two. What's going to happen? For case number two, we're still going to start with the root over here. And we're going to start with, let me use the pink over here. If I start with 44 over here, and I'm looking for 68 over here in this case. 68 is strictly larger than 44. That means I should go to the right hand side, right? That's what I should go. And once I go there, I know that 68 compared with the current root over here, 68 is actually strictly less than the current root. That means we should go to the left subtree over here. And you can see the 68 again is actually not really matching, but it's actually strictly larger than the 65. Meaning that we should actually go to the right hand over here, right? You can see you just gotta keep going. And every time we go for a particular search to either right subtree or left subtree, either right or left, we are going down one level in the tree. That's something, again, you want to note. Right, so what will be the current root? We want to look at 82. And for 82, it's actually strictly larger than 68. So that means 68, what we're looking for, is actually larger than that. And we are facing this one over here, 76. And where should we go? It's not really matching. And we know that 68 is also strictly less than 76. And now it comes to the critical point. We should go to the left subtree for 76, but this particular left node is actually external. So this will be the node to return. It's a failed search. Okay, let me just write it down. It's so important to see the second case. The first case is rather easy to understand because it's a successful search. But a failed search, it may not appear as intuitive at first, but we'll see how useful it can be. So this will be successful search. This will be a failed search, beg your pardon. unsuccessful. Unsuccessful search, meaning that external node is actually returned. And without too much delay, I want to tell you right away intuitively why returning this external node would be so useful. Just give me a moment. I just want to highlight external nodes. You want to see external as opposed to internal over here. Okay, let me put some notes for you right away over here. Hypothetically, let's say I got hold of the reference of this particular external node. What if I simply replace this node over here as 68, which is the key that did not exist in the current tree. If I put 68 over here and add it as a new node, would the resulting tree still be a binary search tree? The answer is yes, because if you still try to do the in-order traversal A, 17, and 21, etc., and you will see that 68 over here, and then 76, 80, 82, and then 88 will still have that sorting property satisfied. So what does this mean? This means that returning this external node over here can be very useful if our intention is really to add a new node into the tree with this non-existing key 68. Think about whenever you want to add something into some collection, that thing better not create any duplicates. In this case, 68 is not meant to really create any duplicates. In that case, once we have identified this particular external node, that's really the correct spot to put this new key over here. That's something I want to tell you verbally, but we're going to see this when we talk about insertion again. Let me just put one little note over here. Okay, that's something you can also think about. Okay, let me put a star over here. Replacing this return external nodes. You know what? I shouldn't say replacing. Let me be more precise. I should say storing this external node with the key 68 maintains the search property. Right, let me just make a little bit more space for myself, and then I'll write it down properly. Maintains the search property. Okay, to really convince yourself, think about what if I put 68 over here. What if, hypothetically, if I put 68 over here, in that case, will the resulting tree still be a binary search tree? And remember what we said before, how to check a binary search tree? You have to make sure the search property is actually maintained. I'll leave you to do that check yourself. All right. And this will be also very important. Storing this return external nodes with the key 68 will maintain the search property. All right. Alrighty, so that's about the visual tracing of the searching a key through the binary search tree. We got the two cases covered. Let's now move on to tracing some Java code.